the function is multiplicative, meaning if two numbers m and n are relatively prime, then we can split this kind of product into individual application of phi function and then multiplication. So this was proved, and the idea was multiplying legitimate columns, right? Number of legitimate columns multiplied by number of entries relatively prime entries in each column, right? And then they are equivalent. So this was the way we proved the theorem. And if you have a question about the way to prove this multiplicity, ask me. Then the next thing we want to cover is a very, very important property called the Euler's theorem. It's the generalization of Fermat. Fermat theorem said if you have a to the power of p minus 1 is congruent to 1 mod p. But here is limitation. First limitation is p should be prime. Right? This is the first limitation. Second limitation is a should not be 0 mod p. So a should not be 0. So we need these conditions. But what if we want to develop something like this for general modulus instead of prime modulus? So if you have n, can we have some similar fact as this one? If we use this thing, then we can relax the condition. First condition is gone because n is general number, not just prime. Second is the same because if a is 0, if no matter how many times you multiply, a to the power of something cannot be 1 because it's 0, right? So the second condition is still required. In other words, instead of these conditions, we need just one condition, right? Then it happens. Then the next question is this. What should be the power in the box? What should be this power? We had a to the power of p minus 1 equals 1, is congruent to 1, then is prime. But as you know, p minus 1 is nothing but phi of prime, right? Phi of p is p minus 1. Do you see? Right? Phi of p is p minus 1. So what about phi of n? What about phi of n? And is it a legitimate guess? And the answer is yes. So Euler's method is nothing but this thing replaced by phi of n. This is Euler's theorem. Then let's check this Euler theorem is really a generalization of Fermat's theorem. So pick a prime. If we pick a prime, then phi of p is what? P minus 1, right? So a to the power of p minus 1 is congruent to 1. So once we learn this Euler theorem, we don't need Fermat's theorem, right? It's the generalization of Fermat's Euler theorem. If you have a question, ask me. If you don't, then I will prove it. But before proving it, let's see an example. Let's see an example. Pick any number. Pick any 2 to 3 digit number. I didn't set this up, so you can pick any number n.
42.
42. Then pick any number a. A which is relatively prime to n. 5, right? 5 is relatively prime to n, right? Do you see it? Then what happens? So I mentioned that this is the mod n is not 0, but this is not enough. As you can see, I will rephrase this portion. This portion will be rephrased. I will say it. The GCD of A and N should be 1, right? It should not have the common factor, right? So I modified this portion, right? I only consider the prime case here, right? In prime case, but in general case, it can have the common GCD, right? It can have the common GCD. So I removed that case. So let's pick this thing then. First of all, what is phi of 42? Phi of 42, I will calculate using MATLAB. Phi of 42 equals 12. Then 5 to the power of 12 is what? This number. And then this number, mod 42 is what? 1. Do you see it? So, as you can see, 5 to the power, right? A to the power of phi n is nothing but 5 to the power of phi of 42, and the phi of 42 is 12. A to the power of 12 is a big number, right? It's a big number. 24414, and then 625, right? This is it, right? So 5 to the power of phi is 5 to the power of 12. 5 to the power of 12 is this one. And then this one is congruent to 1 mod 42. So I didn't set this up. You chose this number, then it became 1. So you may pick other n or other a. So you may pick a combination of n and a. Because we have a computer, you can pick a big number too. So pick 2 numbers. So n equals what? And then a equals what? First choose a, n. Then we can find the relative prime number a. So pick a big number n. Maybe 3-digit number is okay. 240. And then what a do you want? 77, right? So we have n and a. Then let's do it. I create this thing. Power mod 77 to the power of phi of 42, right? Phi of 42. So phi of 240 mod 240. Do you see it? 77 to the power of phi of 240 mod 240. Do you see it or not? So I will run it. Then it is 1. Right? 77. So I will calculate phi of 240. It is 64. So a to the power of n is equal to 77 to the power of phi of 240. And then it is equal to 77 to the power of 64. And then this will be a huge number, right? This will be huge. Then it is congruent to 1 mod 240. So I will pause, and then you may check the idea. Oh, sorry, I wrote down n, but it is not n. It is phi of n. Right? Phi of n. So a to the power of phi of n is always congruent to 1 mod phi. Mod n, right? Mod n. So no matter what n you choose, once you pick a relatively prime base, then relatively prime base to the power of phi of n is always 1. This is Euler's theorem. And very, very important encryption, RSA encryption, depends on this property. Questions?
On the test, if we have problems like this,
Of course, yeah, we will.
but it seems like numbers get really, really big, really, really fast. You know what I mean?
But
Really small numbers?
you have like a binary exponentiation technique. So take a look. If you have 77 to the power of 64, you do 77 to the power of 2, right?
Yeah.
And then 77 to the power of 2 to 70 to the power of 4, and then 8, and so on. But I may use like 2-digit number or 3-digit number. Not, it doesn't go to very big.
Okay.
But if you don't use this technique, it will go big. Even in the previous case, it went very big. If we don't apply the technique, it goes big, right? It goes to a big number very fast. So you should use
P also. It's,
phi is nothing difficult. Phi of 240, then 240 equals, right? This is right? And then 16 times 15, right? Or 16 is 2 to the power of 4 multiplied by 3 by 5, right? Then by the property, it is equal to 240, and then 1 minus 1/2, 1 minus 1/3, 1 minus 1/5, right? So I can use 250 without any limitation. Then it is equal to what? 240, and then this is 1/2, and then this is 2/3, and then this is 4/5. And then as you can see, 2 and 2 are cancelled out. And then 5 can be cancelled out, right? And then it is 48, right? 48. And then these are cancelled out, like 8, 16, and then these multiply 64. So it's not very difficult. So all the necessary calculations were covered. So you can use the necessary calculation techniques to do it. Please practice with 42, phi of 42. You chose 42, so please practice. What is phi of 42? So do you see? So when you have a factorization, then we just factor 1 over those prime factors, right? One of those prime factors multiplied together gives us phi of 42. In any case, we have seen that A of this equals 1 mod n if GCD of an n is equal to 1, right? If we have different GCD, then there is no chance, right? Assume that A and n have common GCD, for say like 2. Then even number power to the power of any power, like any number, cannot be odd, right? Even multiplied and then even mod, then it cannot be odd no matter what. Do you see? So we issue this condition. Then next thing is the proof of this thing. Prove it. Proof. First of all, consider set. So we pick all positive numbers which are relatively prime to the given number n, and then between 1 and n. So for instance, n is given, then 1, right? And some numbers in between, and then in the end n minus 1, right? These kind of numbers are relatively prime to n. We don't know how many, I mean, what kind of numbers will come, but what we know is how many, right? How many numbers can you find in this set? Relatively prime numbers. Relatively prime to n. No. Can you find how many numbers in this set satisfying this condition? Create a set of all numbers that are relatively prime to n, and then between 1 and n. Then how many numbers can you find in this set? Assume that we write this set in this form. Then how many numbers can you find in this set?
Phi of n.
Yes, phi of n. So the number in this set is phi of n is the definition, right? Definition. The number of integers inside the set is called phi of n. If you don't remember the definition, please visit the definition part, right? These are relatively prime numbers to n, and then that is counted in the definition. This is not special thing definition. Phi of n is the number of numbers inside the set satisfying these conditions. Any questions? Then the next step is pick some number satisfying, pick some number, say a, satisfying GCD condition. So we may find any a having satisfying this condition and check it. Will a be inside the set or not? Will a be inside the set? Yes, it should be inside the set, right? It will be inside the set. So we have found a. Now what I want to do is this thing. Multiply everything here by n, a. So a times 1, and then a times something, and then a times something, and then a times something. So everything is multiplied by a times something. Right? So in this sense, how many numbers can you count in this set? Total phi of n numbers, right? And the next thing is this one. Will each of these be relatively prime to n? What is your guess? Will each of these be relatively prime or not? So my question is, pick generic element, right? Pick generic element, say k, right? Pick k. So is a times k relatively prime to n? So this is the question. So because of the condition, I chose k, and then GCD of k and n is 1, right? GCD of k and n is 1. Now, is GCD of a times k and n is 1? That is the question. And what is your guess?
Yes.
Yeah, why? Because last time I proved the condition. Do you remember? If I proved this condition, if an, GCD of an, and then GCD of kn is 1, right? Last time I proved it. GCD of a multiplied by kn is 1, and the other direction is also true. So I completely proved this last time, right? In both directions. But we don't need the other direction here. Just one direction is enough. In other words, all these numbers are relatively prime to n. So we have two sets of phi n numbers, right? Phi of n numbers. First type set, second type set. Then what should we do? All we need to show is to show that these two sets are essentially the same. Only difference is the rearrangement. In other words, there are 45 seats here, and then 45 students were here, and then they went out, and then they came in, and they occupy any seat they can find, right? Then essentially, the set is the same, even though individual position might have different members, right? Different students, right? Do you see it or not? So 45 members here, 45 students out, come in, right? Then we will have the same set of numbers. Then how can you handle this thing in totality instead of individual handling? How can you handle this in any reasonable way? The reasonable way is multiplying first set and second set. So I will call this set 1, and I call the second thing set 2. So I will delete these things, and then I will call this set 1, and then I will call this set 2. Do you see it? There are two different sets, set 1 and set 2. But I multiply set 1 and set 2. Product of set 1 is equal to product of set 2 as sets. Do you see it or not? Mod n, right? As sets, they are the same. Individual members may change, right? Once I ask you to leave this room and then come in and then randomly pick positions, then individual position may have different members, right? Individual position may have different students. But in total, the same students went out and came in. So the same thing. Set 1 and set 2 are different element-wise. But as total, they are the same, right? So as you can see, product of S1 and S2 are congruent. So let's multiply these things. Then 1, and then all these things, and then n minus 1 is the set product of first set. Second is 1, a times 1, and then a times something, right? And so on, and then a times m minus 1, right? They are congruent. You see it? Then take a look. All the elements here are relatively prime to n. All these elements are relatively prime to n. So let's pick generic elements such as k, right? So I want to cancel out k. which is relatively prime to n, then I can get this kind of thing. 1, and then k is missing now, right? K is missing now, and then these kind of things equals a 1, a, and the k is missing here, right? K is missing here, right? K is missing. Not a, k is missing. So a is not missing, only k is missing, right? K is missing. So generally, we can cancel out. We can do the same step, right? Do you see the cancellation rule or not? Do you see the cancellation rule here or not? When you cancel out k, we change the modulus. Modulus should be n over g. Do you see? What is the g? GCD, right? What is the GCD? 1. So we can replace this by mod n, because GCD of k and n is 1. When you apply the cancellation rule, we should divide the modulus by GCD, right? G. But GCD happens to be 1, so it doesn't change. So we can repeat these things for all numbers but a, right? We can repeat these things, all numbers but a. Then what happens is this one. The left side becomes 1 after canceling out everything, right? And then right-hand side has all gone, right? All this is gone, right? A times 1, this is gone, right? And then a times something, this is gone. And then a times k, and then this is gone. And then a times n minus 1, and then n minus 1 is gone, right? Do you see it? So I canceled out all numbers but these a's, right? So eventually what I have is 1 is congruent to a multiplied how many times total? Phi of n times. Done, right? So I completely proved it. So please browse the idea and ask questions. Oh, excuse me. So, as you can see, the key is forming two sets. So this is the key to the proof. Forming two sets is the key to the proof. Once you form two sets, multiply, right? Multiply everything inside the set. Because as sets, they are the same. Entry-wise, we don't know. How can it move? We don't know, right? Entry-wise, once you leave the room and come in, we don't know where you may see it. We don't know. But as set, they are the same, right? As sets, they are the same. And this is the key to the proof, right? So I will write it as sets. They are the same, right? As sets, not element-wise, but as sets. To use that fact, what I did was not individual comparison. What I did was just totality, right? Multiplying everything. Multiplying everything, then we don't even have to mention this thing because we multiply everything. So this is the key to the proof. And once you have this proof, you will see why this plays a role, right? So it's not out of the blue, right? It's very legitimate, right? Because how many entries are in the set? These many entries. So we completely proved Euler theorem, which is the generalization of Fermat theorem. And we already covered the other cases and properties. And finally, I will prove one thing and go to the next chapter. And as I mentioned before, next week, not on Monday but Wednesday, I will review for the exam too. But if you want to ask anything, ask me. You may stop me. Last time I proved this important fact. Phi of n added, sorry, n is not a good word. I will rewrite it. Phi of D added for all divisors, right? Phi of D added for all possible divisors of n is equal to n. I proved it. How did I prove it? I used that the function is multiplicative, right? Then I don't have to prove it for general n. I only need to prove this for p to the power of alpha, right? When it is p to the power of alpha, I proved it using telescopic cancellation, right? Telescopic cancellation. Now, today I will apply the inversion formula, right? So it's called Möbius inversion formula, Möbius inversion. Then what happens? Once we have a sum, once we have individual summand, then we can find the sum, right? Individual summand creates the sum. And the other direction, if you have a sum, then we can find the summand. This is the Möbius inversion principle. And because of Möbius inversion principle, we can say this. Oh, phi of n is nothing but n times d divides n, and then Möbius inversion formula, right? So this is the property that I will prove by applying Möbius inversion. So once you have a summand, we can find the sum. Once you have a sum, we can find the summand. So this is achieved by Möbius inversion formula, and I will prove it. By Möbius inversion formula, f of n is equal to d divides n, and then f of n over d, and then Möbius function u of d. Do you see it? Right, this is the Möbius inversion formula that you can find. You can go to the section covering Möbius inversion formula. And what is the sum? If we add phi function, it is n, right? So it is n, and then this f is n, and then f of n over d is n over d, because it is n, f of n is n, and this was the case. And then Möbius inversion formula creates this one. And then n does not depend on d, so we can extract n, and we will get this thing. And this is the end of the proof, right? So we get this formula. Then by using the multiplicity, we proved that. So this is the end of the proof. Phi of n is f of n, and f of n is f of n. So f of n is phi of n. Capital F of n is n, right? Because of this, we apply the Möbius inversion formula to prove it. Then we're using this thing. We want to derive some formula that we derived before. In the past, we derived this formula. Phi of n equals n multiplied by 1 minus p, 1 over first prime, 1 minus second prime, and so on, right? So we derived this kind of thing before. Do you see it? Right? We derived this thing using the fact that phi is multiplicative. And I even used this thing. I used this thing even today, right? I used this thing even today to find the phi of 240. And I can derive this thing using the previous thing instead of multiplicity. I derived this thing in the first place using multiplicity, but even without multiplicity, I want to derive this thing using this thing. So let's do it. phi of n equals n multiplied by this thing. And this is the previous fact that we proved. And I will decompose n here into prime factors. P1, R1, P2, R2. Oh, R is used here. So I will change this thing to K, sorry. And then PK, RK. And as you can see, mu and d are all multiplicative mu function, and this identity function are all multiplicative. Because these are multiplicative, we can split these things to individual case. So what you can do is using the multiplicity of not phi function but this function. So I didn't use the multiplicity of phi function at all. I only use multiplicity of this mu function and d function. So because it's multiplicative, I can split these things into d dividing P1 R1, right? And then I can split this thing P2 R2. If you don't see the reason, you ask me. And then d divides P R K PK RK, right? RK. So I use the multiplicity of mu over d function, right? Mu of d over d function. If you don't see the reason why, ask me. Because the function u and function d are multiplicative, we can use this fact to split these things for individual fact. Then I can individually handle this thing, and then this thing to derive the fact. So let's consider just one generic prime. So I will use generic prime. You assume that you have p dividing p power of r. Then what are the smallest divisor? 1, right? So mu of 1 over 1. What is the next smallest divisor dividing p to the power of r? Mu of p over p, right? What is the next thing? Mu over of p squared, and so on up to mu of p to the power of r, p to the power of r. Then mu of 1 is what? By definition, mu of 1 is what? Mu of 1 is, by definition, 1. Right? 1 over 1 is 1. What is mu over p? Mu of 1 prime number is negative 1, right? So it is negative 1. And then p. What is mu of p squared? If we see the square, it is 0. If we see any square, it is 0. So if you see any square here, or 0. So because of this reason, we get the result like this. Oh, this is equal to 1 minus 1 over p. Right? This sum is 1 minus 1 over p. Thus, as you can see, we can write these things in this form. Oh, 1 minus 1 over p1, 1 minus 1 over p2, and then 1 minus 1 over pk. Done, right? The same result without using the multiplicity of phi function. I use the multiplicity of mu function and d function, not phi function. So this is the end of this chapter, unless you have a question. And I will begin to cover chapter 8 so that we can finish all these 5 chapters from 4 through 8. So, any questions? Then, chapter 8. Order primitive roots. So, I will define the order. So we say, definition, if k is the smallest number, is the smallest positive number, satisfying then we say that the order of the number A mod n is k. So when we consider the order means the smallest possible number giving this. Of course, we know that this is true for phi of n, but phi of n could be too large, right? A to the power of phi of n is always 1. We know that. It's called Euler's theorem. Special case called the Fermat theorem, right? For general, phi of n is too large. But some possible number, k, exists, right? Some k smaller than phi of n exists. This kind of number is called order. So, to check it, you may pick two numbers. To consider order, we need to consider two numbers, a and n, right? Modulus and specific number, right? Modulus and specific number. So please pick n and a. First pick n. What n do you pick? Pick any n. 65 was chosen. And any relatively prime number, it can be chosen. What number? Relatively prime to this number is okay. 8, right? Do you like 8? So 8. Then, my question is this. Find the order of A. Find the order of A mod n, right? So, this is the case. In other words, find the order of 8. So to do it, what should we do? We should multiply A for one time. So A squared is nothing but A squared. A squared is 64, right? 64 is congruent to negative 1. So is the order 2? Order of 8 is 2 or not? Is the order of 8 is 2? Is the order of 8 2 or not? Order of 8 is not 2 because A squared, right? 8 squared is not 1. By condition, it should be congruent to what? 1. But it is not 1. So, as you can see, order is not 2. Order is not 1. Order is not 2. What about 3? If we see 3, A cubed equals congruent to 8 times A squared, right? A squared. And then 8 times negative 1 is minus 8. And minus 8 is not congruent to 1. So 3 is not the case. Then the next power is 8 to the 4th. 8 to the 4th equals like negative 1 squared. Negative 1 squared is 1, right? And then it's the case, right? Because of this reason, order of this is 4, right? So this is the number. then this is the order, right? Order is 4. So once a number is given with appropriate modulus, then we can find the order. Worst scenario is what? Worst scenario for the relatively prime number A is what? Phi of n. Worst scenario. Why? By Fermat's or Euler's theorem, if we replace this by phi of n, it is 1. So this is the worst scenario. But it can happen way earlier, right? What is phi of 65? I will calculate using MATLAB. Phi of 55 equals 48. We don't have to go all the way to 48. It began earlier, right? It happened earlier than 48. Do you see it? So let's do the same thing with one more example. So please pick another n and a. Please pick another n. 111, right? And then I pick the same a, right? So I chose a different modulus and then different same a. Then what is the order of 8? So to do it, to calculate the order, I will, instead of hand calculation, I will use MATLAB. So let's do it. Power mod 8 to the power of 1 is obvious, power of 2, and then mod 111, right? It is not 1, right? And then power of 3, power of 4, power of 5, power of 6, power of 7. Because it is not easy to write all these things, I will make a loop. So for I running from 1 through like 100, I, and then power of 8, I, 111, right? Do you see this logic or not? Do you see this logic? I do these things from 2 through 7, but instead of doing by hand calculation, I will do these things in the loop, right? I varies from 1 through 100 instead of this. So I will do this thing and then run it. So once I run it, this is order 1, right? Order 1. So I will run it, then let's see it. If I run it, then I see these results, right? So do you see 1? Here I saw 1, right? But it should be the smallest possible number, right? So let's search from the beginning. Smallest possible power is like this. For power 1, it is 8, right? 8 to the power 1 is 8. 8 to the power of 2 is what? 64. 8 to the power of 3 is what? 68. 8 to the power of 4, 5, 6, 7, 8. No, right? 9, 10, 11, 12, right? 12. 12 is the smallest number. So from this, we see that order is 12. Of course, I used computer to find it, but later I will tell you the method that you can use to find these kind of things. So I will pause and then you may check about the definition of the order of a given number. Do you need more examples or not? Do you need more examples of order or not? Do you have a clear picture about order? So order is the smallest. So let's go back to the definition one more time. The smallest integer smallest possible interval satisfying this is called the order, right? So anything comes in here, which is the smallest possible number, giving 1, is called the order. Using this definition and computer, I found the order of 8, right? Order of 8 mod 111. So order of 8 mod 111 is shown here. And then I will clean up this one more time and then show you one more time. So let's do it. Then as you can see, the smallest possible number is not 1. 1 is disqualified, 2 is not, 3 is not, 4 not, 5 not, 6 not, 7 not, 8 not, 9, 10, 11, and then 12 at last. The smallest possible power is 12. And this is the order of the given number 8. So order of given number 8 was 4 in previous modulus, and using this modulus, it is 12. So depending on modulus, order of the same number changes. Right? Order of 8 was 4. Now order of 8 is 12. Assume that I give different number, such as this. Can you expect the order? Find the order of 8 mod 31. Can you guess it? So to do it, I will run my program. So here it is the same 8, but it modulus changed, right? 31, right? Do you see? And then we don't have to go through too many numbers. Just about 30 numbers will be enough. So let's run it. Then as you can see, the first time it appears is somewhere, right? So let's search it. The previous program stopped here. So order 8 to the power of 1 is 8. 8 to the power of 2 is 2. 8 to the power of 3 is 16. 4 is 4. 5 is 1. Right? So order of 8 is 1. So because of this reason, the order of 8 is 1, right? I mean 5. The order of 8 is 5, mod 31. So depending on modulus, we have different order. Order of a fixed number is not fixed. Order of a fixed number depends on modulus. So if the modulus is 65, it is 4. If the modulus is 31, it is 5. If the modulus is 111, it is 12, right? Depending on modulus, order changes. So in my opinion, this is enough for the explanation of the order. Then this isn't the way to find the order, right? You cannot run this kind of program all the time, right? So I will tell you the method of finding it using next slide. But if you have a question, ask me about the order, definition of the order. Then the next thing is, next thing is theorem, and theorem is this. Theorem 8.1. Let K is the order. Let K be the order, right? Let K be the order of A mod n. Then A to the power of H is 1 mod n. Mod n is always assumed if and only if K divides H. So this is just a statement. So I will just write the statement, right? So if k is the order of A, then if some number h satisfies this thing, then k divides h. In other words, anything having right side equal to 1 is nothing but the multiple of k. In other words, if I shorten this thing, then a to the power of this thing, this k, right? K is equal to 1, right? So I will prove the other direction first. And then, first of all, this direction is very easy. This direction, proving this direction is easy. Why? Because a to the power of h, and then k divides h. H is something times k, right? So I'll prove the other direction. A to the power of h is congruent to a to the power of this thing. And then a to the power of this thing is a to the power of k multiplied by this. And then a to the power of k is congruent to 1, right? 1 multiplied many times is 1. So this is the end of the proof of the other direction. Do you see? If you don't see, ask me. If k divides h, then a to the power of h is equal to a to the power of, because h the multiple of k, something times k, right? And then a to the power of k multiply something. A to the power of k is 1, and 1 multiplied as many times is 1, right? So this is the end of the proof of the other direction. Then straightforward direction is a little bit tougher. So please browse the idea and check. And unless you stop me, I will show you the other direction. And the key to the proof of the other direction is very important thing called division algorithm. Right? You learn division algorithm. So let's do it. No questions? Let's do it. So if a to the power of h is congruent to 1, then divide h by k, which is the order, right? H is the number satisfying this, and k is the order. Then if you divide h by k, then there is some quotient, and r, where r is between 0 and k. Division algorithm. If you have a question about division algorithm, ask me. Then, because of this, we can write this thing differently. A to the power of h equals a to the power of qk plus r, and then a to the power of qk, and then a to the power of k multiplied, right? The addition in exponent becomes multiplication, and then this is equal to a to the power of k to the power of q, and then a to the power of r, and then a to the power of k, by definition, is congruent to what? A to the power of k is congruent to what? 1. So 1 multiplied q times, and then a to the power of r. And then, by the condition, this is congruent to 1. By the condition, right? By this condition, it's congruent to 1. So because of this, a to the power of r is congruent to 1 mod n. Then r is chosen between 0 and k. So what should be r? What should be r? R should be an integer between 0 and k minus 1. So what should be r? Can it be some number smaller than k? Can r be smaller than k or not? If you think it's possible, then say it. by definition, order is the what? Smallest number, right? By definition, order is the smallest possible number, by definition, right? Order is the smallest possible number satisfying it. In other words, if you can find anything smaller than this k, then that is the order, not this one, right? Do you see? So assume that you have found k1, which is smaller than k, then k1 is the order, not k. The definition, right? So if r is smaller than k having this thing, then r should be equal to what? Only possibility is 0, right? 0. So r should be 0 because k is the smallest possible, right? The smallest positive number satisfying the condition, right? Satisfying the condition. So if you find any positive number smaller than k satisfying the condition, then our choice of k was wrong, right? Our choice of k was wrong. So it's against the definition. So it's impossible. That means r is 0. Because r is 0, we can rewrite this. We can rewrite this thing. Because r is 0, we can rewrite this thing. That means what? Because r is 0, h equals qk. That means k divides h, and then this is the end of the proof, right? This is the end of the proof. So I completely proved both directions. The other direction is easier. Straightforward direction was harder. So please browse these things and check whether you completely understand the ideas behind this. So division algorithm is extremely important. And in addition to just this fact, it shows us the direction to find the order. What is a to the power of phi of n? A to the power of phi of n is what? A to the power of phi of n is what? 1, right? By what? Euler's theorem, or generalized Fermat theorem, right? A to the power of phi of n is 1. Because of the previous thing, order k must divide phi of n. Do you see it? Right? Order should divide this power, phi of n, by the previous theorem. So this is the special case. Then this can be used to find the order. In other words, idea, right? Idea. To find the order, we need to the divisors phi of n. Not every number. Do you see? We don't have to see every number. We just need to divide. We need to just browse the divisors of n, not all numbers. So it reduces the possible pool of numbers. For instance, let's return back to the previous case. But if you don't understand this reasoning, ask me. So order divides phi of n. Order must divide phi of n. That means if you reverse it, phi of n, from phi of n, order is a divisor of phi of n, right? In phi of n point of view, order is a divisor of phi of n. Why? Because order should divide any number, any power satisfying this condition, right? So this is the key idea to the finding of this thing. So let's check the possible orders for previous cases. For instance, phi of, we considered 31, right? So P of 31. P of 31 is 30, right? So what are the divisors? Divisors of 31. Divisors of P of 31. These are the divisors of P of 31, right? Of course, MATLAB doesn't have divisors function. If you want to call divisors function, download the file. Divisors function. And these are the possible divisors. And then it happened to be what? 5, right? Do you remember it? So next case, we considered 111. And what are the possible divisors? These are the possible divisors. 111, sorry. These are the possible divisors, and then it happened to be 12, right? So instead of searching from 1 through, well, like 100, we need to search through only these numbers. And in the first case, phi of 65, the possible divisors phi of this thing is these numbers, right? And then the order of this thing happened to be 4, right? So we don't have to go through all possible numbers. We only go through the divisors of phi of n. So this is the key. This is the key to the finding of the order. So please browse the ideas and ask questions. So this simple theorem gives us a clue about the method of finding the order. So when you are asked to find the order, all you need to do is finding the divisors of phi of n. Not n, but phi of n. Divisors of phi of n. So I pause, and then you can check these things and ask questions. No questions? Then the next thing, but I felt it's a good idea to give you as many examples as possible. So I will use textbook examples. Textbook used mod 13 with 2. So 2 to the mod, 2 to the power of 1, and then 13. So this is it. So instead of using this kind of thing, I will use a loop. So I will do it using loop. So power is k, and then power mod 2 to the power of k mod 13. Mod 13, right? So this is the one that I will do, and then see. So let's do it. Thank you. So these are the numbers. Take a look. 2 to the power of 1 is 2. 2 to the power of 2 is 4. 2 to the power of 3 is 8. Right? 2 to the power of 4 is 3. 5 is 6. 6 is 12. 7 is 11. 8 is 9. 9 is 5. 10 is 10. 11 is 7. 12 is 1. So the order of this is what? Order of 2 is what? 12. Why? Because this happens here. This is the smallest possible power giving us this number. Do you see it or not? If you don't see it, ask me. So order is the smallest number satisfying this. But now, instead of doing this, let's see divisors, right? So divisors of phi of 13. Then, as you can see, these are the numbers that we need to examine, right? 1, 2, 3, 4, 6, 12. Nothing in between, right? Between 6 and 12, nothing, right? Only these are the numbers that we need to examine. So I will give you a few more examples. But while this happens here, sometimes it happens way earlier. I will use mod 12. With mod 12, I will change these things. I will fix the power, and then I will change the base A. So A base changes, right? So A is 2 times A minus 1, and then mod like this. 13 and 12. I mean 6. So let's do it. I will make it easier. A moves from 1 through 5, 7, 9, and 11. So A varies from 1 through 11, and then I will type A, and then power A squared mod 12. Do you see it or not? So what I want to do is moving A from 1 through 11, and then presenting the number A, and then power of A, right? Power of, for instance, 1, and then like with A squared, 1 squared, 3 squared, and so on, up to 11 squared mod 12. So this is what I will do, and then let's check it. So this is the result. As you can see, 1 has order 1. 3 doesn't have order 1 because 3 squared, 1 has order 1 and 3 has order 2 or not. 3 squared is not 1, so 3 doesn't have order 2. Do you see? What about 5? 5 has order 2, right? So order of 5 is 2. Do you see it or not? 5 squared is 25. 25 o'clock is the same as 1 o'clock, right? And then the next number is 7 o'clock. 7 o'clock squared is 49 o'clock, right? 49 o'clock is 1 o'clock. And the next number is 9. 9 squared is 81. 81 is not 1 o'clock. And the next number is 11. 11 squared is 121. 121 mod 12, right? After eliminating that one is 1 o'clock. So as you can see, we get 1. So order, what does this say? This says, I will use some space to write example and then finish. So example part is good. Order with mod 12, order of 1, 2, 3, 5, right? 5, 7, 11 is 2. So order of 5 is 2, order of 7 is 2, order of 11 is 2 with mod 12. By the definition, right? 1 to the power of 1 is 1, so 1 has order 1 all the time. So it's trivial fact, right? 1, I will write it. The order of 1 is always 1, because 1 to the power of 1 is 1. So we don't have to worry about this trivial fact. But other than 1, 5, 7, 11 has order 2. So let's stop here. And next time, I will cover the primitive root. Maybe about next time we can finish everything in chapter 4 through 5. And then I will begin to go through if we can. But if we cannot, then we may need next Monday.